the next assignment that I was working on, where we had to do advanced dimensionality reduction, and then we had a few ends and whatever we had to do, like on image dataset or like tabular dataset, and these are all of the PCA, LLE, TSNE, everything, isomap, all of the dimensionality reduction methods that we had to do. So, and also this was using Databricks. So let's move to the GitHub repo where I have all of this. So as you can see, so in this I have linear techniques like PCA, randomized PCA, incremental PCA, and the kernel PCA, and then factor analysis. And then also we have the manifold learning techniques, which were the second half, like LLE, MDS, isomap, umap, and then tsname. And then also the non-linear techniques where we used autoencoders. So let's go to the first part where we demonstrated all of this using a Google Colab. So here all of the setup part is done. So like we're just getting a few modules that we require, and then matplotlib, numpy, sklearn, and then this is the PCA process. From here we start with the principal component analysis, and then we're just building a 3D data set over here, and then we'll checking the center, and then doing all of the shaping, reshaping, and then if all of them are close, np.all close, that is showing is true. So this actually in the sample hint that was there was showing as false, but when I tried it was showing as true. So we're just gonna move ahead, since we're doing the SK, like the if they're the same. So basically if it is false, that means the same. If it's true, then they're not the same. So we're just printing a few rows, and then we're just checking if x2d and the x2d using svd are like the same. So just printing the correlations, everything. So here when I checked if the projections were equivalent, it was showing as true, so which makes me assume that I was doing the right thing. Then here we're doing the PCA using scikit-learn. We're doing the principal component analysis. The same thing over here. So if we are doing the direct comparison over here, and this is the flipped axis comparison, so using the direct comparison, it's showing as true, but if it's flipped, then it was showing as false. So I think there was a difference in the data set, since we just generated a random data set, that this was going wrong. I mean not going wrong, but it was showing different results. So this is the inverse transform. We're doing the x3d inverse, then checking, and then here we're doing the reconstruction error, and then we're doing the transformation again, then we're displaying all of the PCA components. So all of these are the, I would say all of these are like the variables that we're just testing. Like here we're doing the explained variance ratio, and then expressing the plane, like we just took a plane and we're expressing it in the terms of x and y, and then here we are plotting the 3D data set. So yeah, as you can see, this is the 2D data set, and then we're taking the Swiss roll data set, which is nothing but it'll be like this. So on that we're doing the PCA. So as you can see, it looks like a Swiss roll, the dessert, so that's how it gets its name. So we're just taking that, and then we're just displaying a scatter plot based on that. So this is the projection onto a plane, and this is the unrolling of the Swiss roll. So if you project the data set as it is onto a plane, it'll look like this, and if you unroll it, basically unwrap, it's gonna look like this. So here we're setting the decision boundary, and then we're plotting a few graphs. So as you can see, the decision boundary is set here. Then if it is set here, then this is how it's gonna look. And then this is the other one where it's probably in the z-axis that we can't see, so it's gonna look like this. Mm, these are all the plots that we're doing. So after the PCA is done, so then here, like, it also matters the number of dimensions which we choose. So we're doing the training, testing, and the PCA is done over here, and then we're just displaying the. And then after that, here we're just displaying an elbow graph to show the variance plot. Then we're doing the PCA for compression. So all of this was the extra code which I just ran to check out. So this is the compression of the image. Then we also have randomized PCA which we had to do, and then incremental PCA. So using incremental PCA, this is the result, and then this is using randomized PCA. And then we're just checking the time complexity. So based on the number of components, the time increases. So this part here, it's to compare the PCA and randomized PCA for data sets of different sizes. So as you can see, randomized PCA is increasing, like the training time increases on a vast scale as the number of examples increase. So this is on 2000 instances. So as you can see, randomized PCA is lower. It takes less time compared to the PCA. This is for kernel PCA. So from sklearn decomposition, we're importing that and then setting up all of the. So we have three kinds. So just to differentiate between linear, RBF, and then sigmoid. And then this is the part we're doing the tuning of the hyperparameters. So yeah, and this is the last part. This is the part where we're using LLE. And then after that, these are all the other reduction techniques like MDS, isomap, tsna, and rest of that. Yeah, these were a few examples. So like exercises that I didn't run, but yeah, till here I think we're fine. So this is all about the dimensional reduction techniques. Thank you.